Hello everyone, today we will see about the solution of homogeneous linear recurrence relations with constant coefficient. So let's start from the first order linear homogeneous recurrence relations. As a definition, the first order linear recurrence relation is defined like this one. The first order linear recurrence relation is an equation of the form like this one, or you can write such a way, where C is any arbitrary constant. One way to solve such a recurrence relation is by substitution or an iteration method. In this method, a given recurrence relation is used over and over again for different values of n, where n plus from 0, 1, 2, until we obtain a closed form formula for the recurrence relation. So that formula will be the solution for the recurrence relation. As we have defined last time, the solution for the recurrence relation is a sequence that satisfies the recurrence relation. So let's see this one with an example. The example says solve the recurrence relation, which is an, which is equal to 2 times an minus 1 with an initial condition a naught, which is equal to 1. So using an iteration method, you will substitute n is equal to 1, 2, 3 up to the nth term. Then we will get a recursive formula which is close to the solution of the given recurrence relation. So when you are n is equal to 1, it becomes 2 times a naught when we substitute n is equal to 1. And when we substitute n is equal to 2, it becomes 2 times a1, where a1 is this one, which is 2 times 2a naught, which is to the power of 2a naught. And a3 will be 2 times a2, then a2 is, we know that the a2 is to the power of 2a naught, then a3 is to the power of 3a naught. So in such a way, an will be 2 times an minus 1. But an minus 1 is defined before, then which will be to the power of n naught, to the power of n naught. Hence, an, which is equal to the power of n naught, is a general solution to the recurrence relation. And since the initial condition is given, we can find the particular solution to this recurrence relation. So substituting a naught is equal to 1 on the general recurrence relation, we get an, which is equal to the power of n, is a particular solution to this first order recurrence relation. So this is a solution for the first example. Let's add another example. Solve the recurrence relation. Solve the recurrence relation an, which is equal to 2 times n minus 1 plus 1 with an initial condition a1 is equal to 1. So by using an iteration method, putting n is equal to 1, 2, 3 in such a way, a2 which is equal to 2a1 plus 1. So a3 will be 2a2 plus 1, but a2 is 2a1 plus 1. Substituting it, you will get this one to the power of 2a1 plus 2 plus 1. So a4 will be 2 a3 plus 1, which is equal to 2 times a3 is this one. So 2 to the power of 2 a1 plus 2 plus 1 plus 1, which is equal to the power of 3 a1 plus 2 to the power of 2 plus 1 plus 1. And a5 is 2 times a4 plus 1, that a4 is defined here, then 2 times a to the power of 3 a1 plus to the power of 2 plus 2 plus 1 plus 1. So which is to the power of 4 a1 plus to the power of 3 plus to the power of 2 plus 1 plus. So clearly you can see that a5, which if it is an, then you will reduce 1, then on this term you will reduce 2, n minus 1, n minus 2, n minus 3, such plus something. So the nth term will be, an will be to the power of n minus 1 plus 1, which is to the power of n minus 1, a1 plus to the power of n minus 2 plus to the power of n minus 3 plus 2 plus 1. So we can write this one in such a way, to the power of n minus 1, a1 plus 1 plus 2 plus to the power of 2 plus to the power of n minus 2. And we know that 1 plus 2 plus to the power of 2 plus to the power of n minus 2, which is equal to the power of n minus 1 plus 1 in basic mathematics for the freshman university students here. And since a1 is 1, so since a1 is 1, an, which is equal to the power of n minus 1 plus to the power of n minus 1 minus 1. See, which implies that an, which is equal to the power of, adding these two terms, you get an, which is equal to the power of n minus 1 is the particular solution for this, the particular solution for the recurrence relation. So another example, let's look at another example. Solve the recurrence relation an, which is equal to an minus 1 plus n with the initial condition a1 is equal to 2. Similarly, substituting n is equal to 1, 2, 3 up to n, we will get the closed form solution for this recurrence relation. So when n is equal to 2, a2 is equal to a1 plus 2. When n is equal to 3, a2 which is plus 3, but a2 is a1 plus 3, so which is a1 plus 2 plus 3. a4 is a3 plus 4, but a3 is a1 plus 2 plus 3, which is a1 plus 2 plus 3 plus 4. In such a way, an is an minus 1 plus n, which is a1 plus 2 plus 3 plus 4 plus like that, plus n. So which is the general solution, and substituting the initial condition, a1 which is equal to 2, we get a particular solution. So now to find that particular solution, let's replace 2 plus 3 plus 4 plus this one. So 2, substituting after that, substituting a1, you'll get 2 plus 3 plus 4 plus n. Now let's split 2 as 1 plus 1. 2 as 1 plus 1, then 1 plus 2 plus 3 plus 4 plus this one is this term, as you have learned in basic mathematics of freshman course. This term is equal to this value. So the an term, the an is the particular solution for this recurrence relation. An is given by 1 plus n times n plus 1 over 2 is the particular solution for the recurrence relation. So on the next section, we will see the solution of second order homogeneous linear recurrence relations.